Yeah. So basically, like I said, I'm worried about few people and actually guys to make sure that you're doing what you're supposed to be doing and not delaying things. Morning, Winter. That you are keeping up with all the work. I know I'm posting a lot of stuff on Canvas, and I'm sorry, on YouTube, but I'm relying on the fact that you guys are actually doing those things. You're not just basically waiting for the homework and started thinking about the lecture. The lecture needs to be done in the sense that you need to go through all of the materials that are posted. Make sure you know how those things work. Make sure you have a full understanding of that. You go back into your book and make sure you follow basically section by section. Nothing is basically left unclear, basically. And if there is a question about anything, you need to really ask the question. That part, for example, of that section, that idea is not clear. Can we go through it? We need to understand it. So the fact that we're meeting face to face should not really prevent us from doing everything we're supposed to be doing in order to really have a full understanding of this material, and also for the exams and all of that thing. So I really I want to make sure that everybody is still on there, and I probably will reach out to you guys. I mean, the group or also on an individual basis to make sure that you really are on top of this material and not falling behind in any way or the other or other. Okay. And I see Winter has the camera on, which is fine. And good. And I see a pen also, and that is actually a good practice. Make sure you're taking notes. You're not basically watching. This is unfortunately not a top-notch Hollywood production where you're going to be entertained and basically kept, basically. So if you're not taking notes, you're going to basically start to drift and lose focus, and that way you're not going to benefit from it. So the thing is, you need to be taking notes manually and following, and if there is something you're not clear, that is the time actually to basically write down something or intervene quickly there and say, hey, can you go through that thing in there? Okay. I know when we are in class, I have a visual of you guys. I'm looking, I'm getting the feedback immediately from you guys by looking at you, and you're looking at me and making sure that something is sinking or not going through, so we can go through it again or do more examples or anything or something like that. But some of the material that we're doing is actually pre-recorded, and some of the stuff we're doing online, I mean together on Zoom, and we're moving on unless somebody says, hey, can we go through this one? And I know some of you were actually very good at this. So I just want to make sure everybody else also is following and doing the work they're supposed to be doing. I don't have any message from anybody, so I'm just checking. And I have, for some reason, we don't have half the class yet. And that's not good. So we really should have everybody in here, okay?
When is exam 4?
Okay, exam 4, most likely, depending on how far we go today, how far we move in today. It's going to be next week, probably most likely on Thursday, okay? Because chapter 29 is still, basically we didn't start it. Just about to start chapter 29, there was a question that Gareth asked the other day. Actually, I asked, and some of you basically, Gareth actually influenced the fact that needs to be clarified from chapter 28, so I need to cover that too before we move on to chapter 29. Chapter 29, you will see, is not really too much content in terms of content in it, but the calculations are actually extremely important, so they are extremely needed. So if we do that today and we move on as much as possible and still do the lab where we cover part of chapter 29 also in the lab because it's part of it there too, then we probably are going to be ready for Thursday where we can do the review materials and stuff like that, and I'll post the questions on Thursday. So Thursday when we meet a week from today, basically just to tell you, okay, here is your stuff, you have this much time to finish it, and submit it, okay? So that's basically how this thing is going to work. Okay. So let me go back. Let me stop the sharing of this thing in here, and let me go back and try to find my notes in here. So today's topic is on chapter 29, and is basically Faraday's law. But before we get into Faraday's law, there was some lingering questions from chapter 28, namely, what are bar magnets basically? We know from chapter 28 that electricity or electrical current creates a magnetic field. That is basically the case. The question now is, a bar magnet or permanent magnet, how is it different from anything else? For that, we have three kinds of magnetic materials we're going to talk about. There are actually far more than three, but we're going to focus on three only. So there is the paramagnetic behavior, paramagnetic. There is different materials exhibit different behavior called diamagnetic. Diamagnetism. And there is the famous one that all of you know, namely ferromagnets, and this is what bar magnets are. They are ferromagnets actually. Okay. Ferro, I don't know, but at least in French, iron is called le fer. And fer, that's basically where the word is coming from, and because basically most of the at least permanent magnets were made from iron. Three materials that exhibit this behavior: permanent magnetism, and that is iron is one of them, and nickel is the other one. I think cobalt is the third one or something. Anyway, it doesn't matter. So, what is paramagnetism? Basically, every atom, of course, you know, has electrons in the outer shell. Some of the atoms, they have an odd number of electrons at the end of the outer shell. Those odd numbers of electrons, like for example, like metals, for example, what they do in this case, that outer electron has a property called the spin. You can think of it like, for example, when the Earth is going around its axis, but just that's an image. It's not really a picture. It's not correct. Okay, 100%. It's a fundamental property. Like, for example, somebody asks, what's the mass of the the electron? You give them a number, 10 to the negative 31 kilograms. They ask you, what's its charge? 1.6 times 10 to the negative 19. What is the spin of the electron? It's either a positive or negative 1/2 in the units, basically, in quantum mechanical units. So, it's a property, okay? It's kind of weird, I mean, to say it that way, because what is 1/2, that's something else for physics 252, I guess, or the next physics. Anyway, so it's a property as if the electron itself is moving around its own axis and basically appears to be like a current. So you can approximate it as such. And in doing so, basically, if it's spinning, let's say, for example, counterclockwise, its spin is pointing upward. If it's moving in the opposite direction, its spin is pointing downward. And that creates, in a sense, a dipole, a magnetic dipole, a north pole and south pole. Creates magnetism, basically. Now, you take that atom, or a bunch of atoms, they're basically what the material is. You have a lot of them. You have about an Avogadro number of them, and you put them inside a magnetic field. Now, the electrons that were flipped, they were rotating this way. Let's say, for example, the magnetic field is pointing upward. They will spin, they will change their orientation, and they align themselves basically because of the fact that if you have a dipole, a magnetic dipole, mu, that is going to be subject to the torque tau. And that torque tau, if you guys remember from chapter 27, that it's given by this expression. So now, basically, if it was anti-parallel to the magnetic field, then it's going to flip because of this torque and switch it to go and become parallel to the magnetic field. So imagine all of the electrons, basically the outer electrons in the atom, they're all flipping themselves, so that results in a net magnetization. Basically, the material becomes magnetized in the same direction as the applied magnetic field. Now, when you remove the magnetic field, now when you take the magnet and put it away, the material is basically, because of the thermal agitation, because of the temperature inside, and the atoms are moving here and there, all of the electrons basically will start moving in random directions, and the net magnetization basically becomes zero. If this one is going this way, this electron is going this way, this electron is going this way, this electron, so you add them all up, you average them because there's a huge number of them, it's going to be zero. So that's paramagnetism, basically. What paramagnetism is, the spin, all of it orients itself with the applied magnetic field. Now you remove the magnetic field and they all go in random directions, and the net is zero. And so that's one effect. Most of the materials, especially with a single electron or an odd electron in the odd number of electrons in the outer shell, they do that. They exhibit this one. Now, there is another behavior actually, it's related to the atom itself, because these electrons are in motion around the atom, around the nucleus of the atom. So as they are also, they are creating, well, you can approximate them into a current, so they have actually a magnetic moment also mu around the atom. Now, it's very hard to take an atom with a bunch of basically electrons around it, not just the ones in the outer shell, but also the ones in the inner shell, and also because of the nucleus, and try to flip it with the magnetic field. Very hard to do. That's why paramagnetism is related just to the electrons, just they can flip back and forth. And since they are not paired with any other electrons, they can do that easily. But if you have two electrons, basically, if you have one electron, is two of them, now we have an even number of them at the end, and they need to occupy the same energy level, then there is a principle in quantum mechanics called the Pauli principle, that they cannot do that. They cannot coexist in the same energy level. So one of them has to flip its magnetic field. So when you apply an external magnetic field, those two, they don't do anything. They have a net current basically of zero. Net, they cancel, their spins cancel. So in this case, you don't have any mu. So you apply a magnetic field in any direction. The ones that are paired, they don't do anything. They are basically nothing is happening in that. So in the case of the atoms that have an even number, they don't exhibit the paramagnetism as much as at least they don't compared to the ones that do have an odd number of electrons. Then those, they are ready to flip. You cannot flip the entire atom. It's not, you require a lot of energy to do that versus just an electron, which is easy to do. But in diamagnetism, that happens actually in all materials where you have an odd number or an even number of electrons in the outer shell. So basically what diamagnetism is the following. If the electron is spinning, let's say, for example, counterclockwise. Well, counterclockwise, if it's a positive charge, it should have a magnetic moment pointing upward, but the electron is not positive. So its mu is actually pointing down. Because if the current is going counterclockwise, then it's going to produce a magnetic field in opposite, as if it's a positive charge moving in the opposite direction clockwise. In this case, that's its mu, is pointing again applied field, which is pointing upward. Once you apply a magnetic field upward, here is a problem now. You have a different problem, and we're going to use classical mechanics, which is not correct, actually, theory, but at least gives us an idea what diamagnetism is. So basically, you have an electron moving in this direction, counterclockwise, and its mu is actually going down, and the applied magnetic field is upward. Now its velocity is this way. Okay, remember, it's a velocity that way. You have applied the magnetic field upward, the velocity is going into the screen, so you have V crossed with B upward, to give me, if the charge is positive, a net force pointing outward from the atom, okay, from the center of the atom, as if the charge of the electron is positive and applying the right-hand rule, okay, you have the charge going into the V going into the screen, magnetic field is upward, and the force will be pointing away from the atom. But the charge is negative, so I have to reverse this force, and this becomes the centripetal force, if you wish. So now the electron is actually going to be pushed into the atom. So what it does, from physics 1, if a particle needs to retain its orbital motion, basically in circular motion, and you basically drag it further, then it needs to speed up. So it needs to move faster, basically. So in order for it to move faster, to maintain its orbit, basically to stay in that energy level. So when you apply magnetic field upward, its V increases. That means the net current now increases. because remember, V is for the electron, now the current is increases. So this magnetization that was earlier, the mu that was there, will increase basically by an amount, because now you have more current, because the electron needs to move faster because of this effect. You guys see the in here? So you apply a magnetic field in here, the magnetization is opposite to the magnetic field. Now, you say, okay, I have some other atoms moving in the opposite direction. Well, it's still the same thing, okay? So in this case, actually, if the magnetic field is applied, I'm sorry, let's keep the atom in here. So if the magnetic field is opposite in this direction, so, and in this case, the magnetic field is pointing upward, I mean, the mu is pointing upward, because, what is the picture in here? I'm sorry, the mu is still downward, okay? Because again, it's a negative charge going this way as if it's a positive charge moving in the opposite direction. Now, if you apply a magnetic field in here, it's going to try to decrease that value. And now you have the centripetal force now, because again, the charge is going inward, the magnetic field is coming down, okay? It's raining down now. We took it the opposite to earlier. So the force is actually pulling toward this one, had the charge been positive, but the charge is negative. So the force actually now is going to be outward. So the electron has to slow down a little bit. Okay, because the centripetal force now is, the force now is opposite to the direction of the central direction. So it has to slow down. In a sense, now the mu is going to be less, because now there is less current. So if I apply magnetic field in this direction, I see the response of the material is as if it's magnetized in the opposite direction upward. If I apply it upward, the magnetization increases downward. So it's always the increases in the which way is magnetized is going to be opposed to the magnetic field. So this is why the first one, para, due to the electrons, they're parallel. So the magnetization is parallel to the magnetic field. Diamagnetism is always opposite to the direction of the applied magnetism. So it has some interesting applications. I don't know if you saw the picture of the lead-headed frog and all kinds of other applications. But of course, it has other applications than just playing with frogs. But the point in here is diamagnetism, because it involves the entire atom, is a lot weaker than paramagnetism. Diamagnetism exists all the time because charges move around the atom all the time. If I apply a magnetic field in one direction or the other, it doesn't matter. There is diamagnetism, which is basically opposite to the applied magnetic field. Paramagnetism, though, applies only to the case when I have an odd number of electrons in the atom. And that is the only case when it applies. Paramagnetism is much stronger than diamagnetism, and that's why it always dominates if it's present. Several orders of magnitude is bigger than diamagnetism, but when it's not there, like for example, when I have an even number of atoms, then in that case it becomes present. It becomes the only thing then in town. If the dominant doesn't appear, then the weaker one becomes present. Now, ferromagnetism, though, is a different story. Ferromagnetism, you apply a magnetic field. Again, it's due to the outer electrons, basically. You apply a magnetic field in this case, and of course, first of all, let's look at it in terms of electrons basically by themselves in atoms. Entire regions now, not just a single atom behavior. This is an entire region of the material itself starts to work together. So you have an electron in one atom moving one way just because you have an external applied field now. So basically it has oriented them so that now you have the mu for all of them in one direction or the other. I took them to be moving all of them counterclockwise, basically. So in this region where the two atoms meet, I have this electron moving this way and this electron moving that way, so they cancel each other. So where the two meet, they cancel. The same thing, this electron is moving this way and this electron moving that way, so they cancel. This electron cancels the other electron. So the region, the inner region cancels out, but the net region outside, I have as if a current for the entire region. So I have a domain now where the electrons basically are moving around the entire domain in such a way now I have a magnetization. I have a big mu now that is a contribution of several atoms now. If I take my material now and break it down into several regions, this is one region that overall the magnetization is pointing this way. This is another region the magnetization is this way. These regions are called domains, actually. This domain is pointing that way. That domain is pointing this way, and so on and so forth. So for ferromagnetic materials, this behavior becomes for entire regions basically working together. When you apply an external magnetic field, most of the domains basically now they orient themselves in one direction. So if I apply a magnetic field, let's say for example upward, this way, so most of the domains start to line themselves more or less in that direction, okay, with the applied magnetic field. So the ones that are completely opposite to it, they start to adjust. The ones that were already close from it, they adjust. And basically the material itself will gain a magnetization that is parallel to the magnetic field. With this three types of elements and some of the compounds or alloys also, if you remove the magnetization, they retain their magnetism. If you remove this B field, the external field, they stay magnetized in what is called the self-consistent solution, basically. Some regions, this region, for example, this domain is supported by this domain to make it stay in parallel, and the other one, actually this one also is supported by this one. Neighboring domains start to help one another to remain in one direction or the other. So now that's basically how permanent magnets work, because now you remove the cause of magnetism, what caused them to be magnetized to begin with, and retain their magnetism. You take this one and you put it under a furnace, you heat it up, and then the atoms start to move around everywhere because of the rising temperature, and then they become random again and you lose their magnetism. They lose their magnetism. I was in middle school actually, and it was a very cold day like this one, decent days in here. And I had a magnet and I put it on my spoon and then I put it on the fire and then I lost my magnetism. I was really, really, really disappointed. So I asked my science teacher and he told me basically it has to do with this thing. Anyway, the point being in here is that's basically how you have a permanent magnet versus what is called ferromagnet than the other two. The other two phenomenon, once you remove the magnetism, magnetic field, they're gone. I mean, the applications for this one has a lot of, I mean, the idea of domains, for example, data storage was a big deal. It continues to be a big deal, and that's why you have hard drives, especially the old type of hard drives, not the optical devices nowadays, that they use this technology to store data, basically, and read data. So during the data storage, basically you have a magnetization depending on the information which is stored in these domains. During the when the material, the disk, what is the disk of the hard drive itself spins around the needle that reads it, actually it reads different magnetization and induces a current in it, which is a topic of chapter 29, I'm sorry, and how basically you read and extract the information from that. So that was a question from last chapter 28. Hopefully that answers that question and you guys were done with the chapter, at least conceptually. This talk, usually we don't do much with it. This is actually part of a different branch of physics called solid state physics. If you guys are taking that stuff, then you will have a lot of applications in there and models trying to explain these things and things like that. Okay? We're done with chapter 28. Any other questions for chapter 28? You have the homework and you have everything. No? Let me make sure to see who's here. We only have, where is the rest of everybody in here? Let me check quickly Canvas to see if anybody is sent a message that they're having difficulty or something. Because usually we have some people who are consistent in here. I see that there are 2 messages, but they are not from you guys. From your class. That's worrisome.
I do know I heard from a classmate in one of my other classes. I'm not sure if they're in this class, but they were getting snowed in and we're probably going to lose power. So maybe that's possible.
The weather is very bad. You're right. So, okay, it's recorded anyway, so hopefully they will not miss much and they will do things. And I will try to reach out later on to them. I know Julian has been in contact with me this morning, but for some reason I don't see him and he didn't send anything. Okay. Anyway, we're going to go into the new chapter, and the new chapter, I think you're still looking at the screen with the new chapter, isn't it? This is chapter 29. For some reason, it stopped working for me, so I'll have to stop sharing. And, oh, there's no sharing in here, so let me share the screen in here. Okay, that's not good. It's not responding. I hate it when it does that, because sometimes this screen, so I'd have to restart the. Okay, good. Now we can look at this material now. So let me go back in here. Okay, so this is stuff from chapter 29. Chapter 29 deals basically with the idea of how can we create a current using the magnetic field. That's basically what Faraday's law is. How can we create an electric field from the magnetic field? Let me explain where this idea stems from. Okay, there are two people at least who published their work later on, Faraday and Henry. One of them in the United States and the other one is in England. And the law now is known as Faraday Lenz law, and you will see where the lens is. Okay, where Lenz comes into, at least most textbooks they call it that way, but they also, Henry worked on it in here in the United States and was in a separate work, and it's the same thing. So, Amperes law basically states the following. The circulation of the magnetic field over a closed path is equal to mu0 times I enclosed. This was just the fresh chapter that we finished. If you think about it, this is what's going on. An electric field creates current. Charges, you have difference of potential, you have an EMF, battery basically, where there is an electric field in there that forces the charges to move. So now the current is actually due to an electric field. So E creates this guy, okay? Now, this guy, on the other hand, is the reason being you have a circulation of the magnetic field. Now, if you have a current in a wire, you have a magnetic field. So Amperes law basically says that in order to have a magnetism, you need to have, in order to have a magnetic field, you need to have a current or an electric field, basically. So Faraday and the people around his time, they were thinking, maybe I can create an electric field from magnetic field. So they started experimenting with it. So what turns out to be is the following. This is, again, an experimental law, okay? The following, that yes, you can create an electric field in such a way, you basically create a battery out of it in such a way that the EMF, so this is an EMF, okay, is given by, I'm going to leave a space in here, the rate at which the flux of the magnetic field changes in an area. So you need magnetic field, but if the magnet is sitting still, I'm trying to pull my magnet in here. Oh man. This is a magnet. If this magnet is sitting still doing nothing, and if you have a wire in here, where is the conducting wire in here? Let me put this thing in here. In here. And if they are stationary, nothing happens. If I have a galvanometer in here, which is sensitive to small currents attached to this wire, nothing happens. I don't know. Okay? I will not measure any current, significant or none. I will not have any current, at least if they are fixed. Now, if this magnet starts to move in or out of the area, its field lines are either increasing in here, assuming that this is a North Pole. Okay, there are more and more field lines now are going in. Now, if this is the South Pole, actually more and more field lines are dragged in. You guys see that? Or if this is the North Pole, and I'm moving away from it, it's dragging with it more and more field lines this way. But if it's the south pole, I'm sorry, not dragging. It's not pushing as much field lines. Let's put it this way. If I have a north pole in here and I'm moving it this way, it's not having as many field lines as it had when it was closer. Now it has a lot of field lines. So the field line starts to decrease. I'm going to draw the picture so that you can see how it looks like. If this were a negative, south pole, and I'm moving it this way, it's again dragging less and less field lines when I'm moving it this way. Okay, so in other words, the positive number is increasing in here. When you subtract the negative number, so it's going to be more and more positive. Okay? So it all depends on the time thing. Now, this picture could be reversed. I could have the magnet sitting by itself, and I could have the wire coming in or coming out. Okay? As long as there is a change in the rate at which the field lines are changing for the magnetic field. I have a flux that is changing with time. If I do that, then the galvanometer starts to go all over the place. I can find even the voltage. If I put a resistor there, basically, and see how much I have a current times the resistance, that's actually the EMF. I have like a battery, basically, without a battery. I have a current that was created on a wire without having any power source whatsoever, without having to plug it into the wall or anything like that. So basically, I have a battery. So this is how you create a battery. Now, the reason why I left this space in here is because of a very important thing. So this is called Faraday's Law. Mr. Lenz came in and said, you know what, I don't like it. It's better to be this way. So he added a negative sign. Just because of that, now this is now known as Faraday Lenz law. Okay, just because of that sign. And the sign actually is not just that trivial. It is actually where a lot of work needs to be done. So, and we'll talk about what these things are. Okay, so this is observation. This is an experiment. Okay, so this is what observation has shown us. So let's talk about all of this, trying to understand them. First of all, what is the flux of the magnetic field? The flux of the magnetic field over any surface is given by the integral of BdA. Okay? This is not a closed surface. If it's closed surface, if you close the surface, there is no flux. That is because monopoles do not exist. So at the end of the day, that's going to be zero. Change it in time or don't, doesn't matter. Okay? So this is a critical piece of detail in here, that this integral is an open integral, that this surface is like a piece of paper, for example, where you have this is a surface that we're doing the integral on. We're not doing it on a closed surface. If we do it on a closed surface, then we have a problem. Then that's going to be zero. So that's what the flux is. So this is the flux of the magnetic field over an open surface. Okay? Go and get yourselves a goat. After you do whatever you want to do with it, take its skin and open it. So that's basically what we're talking about, okay? Don't do that, okay? Okay. So basically, that's what the surface is. So think of it, that's the surface we're talking about. We're not talking about a basketball. Okay. Now, in terms of the EMF, basically, the EMF actually is the circulation of the magnetic field over path. So the EMF in here, and I know probably we didn't go into detail in it when we were doing the lecture when we first introduced batteries. It's basically this quantity. It's like when I do basically the voltage drop from the point of the starting from the battery and come back all the way to it. That is basically how we circulate through the entire path in here, and that value is basically how much the drop in potential is going from point to point to point to point is actually your battery in this case. Okay, so remember when we were calculating the electric potential, and we said that E derives from a potential. the electric field derives from a potential. And then we basically calculated V as being the integral of with a negative sign because of that negative sign, because that's basically what we use for conservation of the energy of EDL. Okay, that was from the first few chapters. I think the second or the third chapter in electrostatics. And now if we go around it, so the only value that remains in this case is that of the battery, and that is going to be your EMF. That's how much electromotor force in here you have. And the electromotor, so this is the EMF. It's like the battery. So what you have in this case in here, actually you have a process of making batteries. All you have to do is get a magnet and find the rate at which the flux of that magnet changes in an area. That is going to induce an EMF. So if you have a wire, it's going to have a current. And if you have a resistor there, you can find actually how much that current is going to be in that wire. So you can find exactly the value of that current is. So you can induce a current in there as if you have a battery. So this is in lieu of a battery, you can do that. As a matter of fact, the whole process works backwards. How do we get our power supply to our homes and to our basically businesses, to our cities? It's through this law. When you go to a Hoover Dam, for example, near Vegas, that is basically the principle with which they operate. They have big, basically turbines that turn inside the big magnets, and they're made up of wires that we're going to talk about them. And those generate electricity. They store that electricity, they distribute it, and that's how we get it. So this is actually the process with which we get most of our electricity. I know we have other processes nowadays using solar panels and other techniques, but at least this is how we get most of our power in our homes and businesses, and what powers the vast majority of our cities is this law. So do you guys have an understanding, at least some understanding of this one? Because we still have to deal with that negative sign, because it's critical, that negative sign. Because once you induce a current in a wire, there are two possibilities for the current to go through the wire. Basically, if this is my wire, and I'm going to make it like to look like a loop, and I can change the magnet in here one way or the other, the current will flow in one direction or the other. So we need to determine the sign of that current. So the method of calculating anything in this chapter using this technique is to do the following. Ignore the sign first of all completely. So if we're going to solve the problems in this chapter, the first step is to ignore the sign. So there are two-step process. First is ignore the negative sign. Just basically find the absolute value of the EMF and use it as a battery trying to find your current or whatever you need to. And so that's going to be just your rate at which the flux of the magnetic field is changing with time, okay? If you have a flux that was given to you, if you can calculate it, if you can do something with it, just take that one in absolute value. Don't worry about which direction the EMF is pointing in order for the current to flow. Once you do that, then you have to deal with the sign. Then you have to once you have a numerical value. So the unit for this thing is going to be actually in volts, okay? So it's a battery, okay? Once you have that, then the question is, which way it's going to flow? That's when you have to go to step 2, deal with the sign. So let's put that sign in here. This is where Lenz law comes in, okay? And let's put it in words. It's going to be a very big mouthful. I know we have it recorded, so hopefully we can write it down too, because it's very important. Okay. In a region where the flux of the magnetic field changes, an electromotor force, an EMF, will be induced. That is, first of all, equal to the rate at which the rate of the flux is changing, the magnetic flux is changing. And its sign is such a way that if it can drive a current, that current will create a magnetic field whose field lines oppose the increase or the decrease in the field lines of the field that created it to begin with. Sound a lot, doesn't it? Yes? I don't see any feedback in here, and I don't see my chat in here for some reason. Nobody's reacting to this. For some reason, I don't have any feedback from the... let me check quickly to see what's going on with my class, because for some reason I have less than half the class, and I don't like very much that. Jackson, I don't hear much from you. Okay, we have another person who joined us. Okay. Okay, so basically, let's talk about this thing in here, because it needs to be clarified in terms of the sign. And I need now, through the chat, everybody is going to tell me one way or the other, okay? So, I have a wire. This is a wire. It has no battery, no current, no nothing in it, okay? Just a wire, okay? Copper wire, if you like, okay? Connected. It's a loop wire. And I have a bar magnet in here. This is the north for the magnet and the south for the magnet. Of course, you know that the field lines are pointing this way. And here, we don't care about the south part, because the field lines are going to come to it anyway. Okay. I'm going to assume that the bar magnet is going toward the loop. So this is the velocity with which it's moving. Uniform, non-uniform, doesn't matter. If I keep them this way, there will be no current flowing through the wire, okay? If I keep them like that. So I need to know, I don't care about the magnitude. The magnitude has to do with the strength of the magnetic field times the velocity in here. Okay, so that's, the times the velocity divided by some, doesn't matter. It's the rate, basically, at which this is flowing. It's moving with the velocity v, it has to do with that velocity v. So I have a wire sitting in here, and I have a bar magnet with a north pole pointing toward the wire, moving towards it. The question is, two choices. Is the current going to flow counterclockwise, or CC, or clockwise C? And I need to see the answer. If you can try it with your own thing. Okay. Remember, the EMF that is produced in here to produce the current would be in such a way to decrease, because there are more field lines going in now when the wire is going through. So it's going to create its current in such a way, if that current creates a magnetic field, it's going to oppose the ever-increasing field lines. So if there are, let's say, for example, 10 field lines right now are coming in, the next motion will bring, let's say, for example, 5 more, for a total of 15. This one has to bring 5 in the opposite direction to keep the number of 10 unchanged. So if now 15 are going in, I need to maintain 10. So this one will have 5 more opposite to that increase to opposite that one. So which way the current is going to go? Is it going to go counterclockwise to do that effect, or is it going to be clockwise to do that effect? So you guys think about it, and I need to know. All of you. This is not a... Okay. Tim already locked in an answer. Winter. Okay, Jonathan. Everybody. You can just type it in there. Jackson and Sophia. You don't have to, just type one letter. You don't have to type the whole thing. Sophia. Okay. So, CC. Jackson. Okay, maybe. You want to enter your answer too? No? Okay. Let's see. So some of you think it's going to be counterclockwise and some of you think it's going to be clockwise. So again, when you're looking at the screen, probably it's going to be reversed as far as you're concerned because of the optics, basically. I'm going to stop the screen, this one in here, so let's just see exactly how it's. Okay. So I have a wire in here. Okay. And I'm going to bring a magnet in here. I'm going to use this pen in here. And let's say this is the North Pole. So let's say, for example, there are 10 field lines already and coming from this wire. I mean, coming to this wire from this magnet. Wire doesn't produce any, if this is sitting still, this will not have any current, therefore it will not have any magnetism. But if this one now is moving towards it, then there are more and more field lines. So instead of 10, now it's 15, now it's 20, now it's 25, now it's 30, and so on and so forth. So this one now will have to produce its own current in such a way to make it so that it's opposing. So if this is pointing toward this side, the other one will make it in such a way it's going to be pointing that way. So its North Pole needs to be this way, pointing this way, to produce its own fields moving this way, basically. So it's going to oppose this change in here, this increase in the field lines. So it's going to maintain the field lines the same number that we started with. So magnetism has to be this way now for this bar magnet, okay? For this loop that is created, that is coming from Amperes Law now. So for it to create the magnetism in this way, if you guys remember from the problem of the loop creating its own magnetic field, it has to point in this direction, okay? So that is going to be a counterclockwise. So those who answer is going to be counterclockwise, of course, correct, okay? But again, it needs some thinking. It's really that obvious. It's not that obvious. Let's, for example, do the opposite direction. Let's say, for example, I have the South Pole now coming this way. Of course, we predict now it's going to be no problem trying to understand this way. So now if I take this magnet and flip it around, let me go back. You're still looking at the screen in here? So if I take this bar magnet now and do the opposite experiment. By the way, this question happens a lot, so you guys need to. So if I have the South Pole now in here and the North Pole in here, and still the wire by itself in here, and the South Pole is where the field line needs to go. And let's say, for example, 10 field lines are already coming into the bar magnet when I start with. And as I push it forward, now less and less field lines are actually going to be pushing in. So this one needs to compensate for the ever decreasing field lines. And remember, the sign in here matters. So it needs to produce its magnetism in the opposite direction. So in this case, it's going to basically run a current in the opposite direction. So in this case, it's going to be clockwise. Correct?
Wait, the magnetic fields are pointing in towards the north side?
I'm sorry. Oh, man, I had them backward. You're right. I have them backward. So all of these magnets are pointing in the wrong direction. So they need to be pointing in the opposite direction. Thank you. So they are pointing actually still this way, but the magnet is actually being dragged in the opposite direction. I'm glad you picked up on that. Okay. Somebody is already locked in the answer. I need the others too. There should be consensus now. Okay. Who wants to volunteer to explain it to me by sharing their screen? So there are now 15 of them. So this one needs to create its magnetic field opposite actually to it. So yeah, the first time we had it correct. Okay. So now we have more and more field lines pushing this way. When we move it this way, so there are less and less of them, so it needs to compensate for it, so it has to run also counterclockwise. So in this situation also, it's going to be running it this way too, okay? And again, I'll have to think about this and make sure that you guys get the correct answer. I don't want you to get the wrong answer, okay? And usually, that's really what the confusion is. Sometimes it's those things in there, and you have to use this negative sign properly. Okay. Yes, did I confuse you more? I'm sorry about this, okay? Yes? Should we move on?
It just goes opposite of the direction of the magnetic field. Or
Not the magnetic field, the change in the magnetic field lines.
Okay.
So the field lines, when the North Pole was pointing this way, coming more and more of them. So it's going to create its magnetism in the opposite direction to compensate for it. So if they were, oh man, I have my left hand, so probably I should, yeah. So it should run its current this way to push it that way. So that's correct. So we had it correct in the first time, clockwise. Now, if I have more and more, so the magnet now has the north moving this way, okay? So less and field lines, oh, I'm sorry, yeah, you're right, you have it correct. So there are less and less field lines moving this way. So there are less and less on the other side. So it needs to push more field lines this way. So it's going to run the current counterclockwise. So it's going to run clockwise. So you guys get it correct. So you had it correct. I'm sorry. It's my fault. So because the bar magnet now is this way and it's moving away. So there are less and less field lines running through it in this direction. So it needs to compensate for those in that direction by making more and more of them in that direction. Do you guys see that? So it needs to run the current now in that opposite direction to make up for the ones that are leaving. So yes, you guys got it correct. So the answer is correct, yes. So the first situation completely you had it correct. So when the bar magnet was going in, then in this case it creates its own to opposite that increasing field lines when the North Pole pointing this way. With the South Pole pointing this way, it was basically it needed to compensate for them by running the current clockwise. When the North Pole is pointing this way and the bar magnet is dragging this in the opposite direction, it's taking more and more field lines of it, so it's going to compensate by making its own in the opposite direction and running the current the way that you guys had it clockwise. Now, if I have it flipped around so that the negative is actually moving this way, so now it has to go in the opposite direction, which is clockwise. Does this clarify it?
Yes.
Okay. Everybody else, you can vote in. You don't have to go with the sound in here. I need at least a few more confirmations. Otherwise, we're not going to move from this point until you have it clear because it's a big deal.
So can we just use like the thumb with the finger wrapping around our hand rule?
Yes, the trouble with it, Sophia, is that you will have different loops and you will have some problems in the homework actually, and possibly also part of your stuff. That it needs you need to really get on top of this sign convention big time, because you will have, for example, a region of the magnetic field lines going into the surface and others coming out of the surface in space, and you'll have wires wrapped around them in some sort of a circuit, and then that portion of the wire is basically has currents pushing one way, as if I have a battery with its polarity pointing in one direction. The other one may have one another in another direction, and now you're trying to find the flux in that region and the flux in the other region, and find the EMF, which way it pulls, and the direction of the current overall. Before you even start doing the circuits, Kirchhoff's rules, you really have to have an understanding of which way the batteries are actually oriented, which way are pointing, in order for you to do any calculation with currents or some other stuff that is in that circuit. Okay. Again, Jackson, I'm glad you're back with us. Okay. So we have a loop here, has no current in it, and now I have a bar magnet. My thumb in here is the North Pole. So this is North Pole. If I'm moving it toward it, more and more field lines are coming this way. So there are more and more field lines pushing this way. So it wants to create its own current, in this case, to opposite that change. So it's going to make its own North Pole opposite to that North Pole. So it's going to compensate for it by having a current running clockwise, counterclockwise, and the direction of its own magnetic field point that way to have a flux canceling the increasing flux in this direction. So this is like an inertia, really, like the mass, for example, when you guys have it in physics 1. So it's opposing that. So that's what the negative sign is doing in here. Now, when I have the North Pole but moving in the opposite direction, like the situation that we have right now, we're talking about it, more and more field lines are basically leaving it. They're going in this direction. So there were a lot of them in this way. So it's going to compensate for them by running a current now in such a direction to have them compensate for the ones that are missing. So it's going to run it clockwise, okay? So it's going to create its own magnetic field to opposite that one. So again, to answer your question, Sophia, it's not against the magnetic field. The magnetic field in both situations is pointing in this direction. In the first situation, its own magnetic field was against it, but in the second situation, the magnetic field was actually in the same direction as that of the magnetic field. It's not the direction of the magnetic field that matters, it's the rate at which the direction at which these field lines are either increasing or decreasing.
Okay.
Okay?
Mm-hmm.
So that is where the sign is. So don't think in terms of where the magnetic field is pointing and say, oh, you know what, I know what the answer is. That's not obvious. You have to find out, are they increasing or are they decreasing? You guys understand that? That's really how this thing works. Does it make better sense not to you, Jackson? Okay, good. Now, I want you again to read through the chapter section, try to understand that the biggest headache is that minus sign. I mean, some people, when they see that law and they say, okay, it seems like somebody did a lot of work and somebody else came in and put a negative sign, and now all of a sudden that law has his name on it. And it's not more, it's more than that, okay? Faraday and Henry and other people actually worked on changing fluxes and finding the currents and basically finding this quantitative law, but it's the sign really later on that determines a lot of things. That's why the name Lenz in here is attached to this one. It has because of that minus sign. That minus sign has to do with everything that I've been talking about. That's really the source of the headache. It's not anything else. So let's talk about the generator quickly, and I think that's the bulk of this chapter. Okay, it's going to be the generator, and after that there will be some applications, and that's it. So the power generator can be thought of as following. Okay, Sophia, if you can turn off the microphone, please, or somebody else, because it's coming back, or Winter has a microphone off. Okay, very good, thank you. So basically, if we have this is how this works. So basically, I have a magnet in here. Think of it as a permanent magnet, okay? Permanent magnet. I have, let's say, for example, the north in here and the south in here. So what I have in this region, I have a wire. I'm going to make it just a single wire, okay? But in reality, it's more than that. Oops, I have a turn on the drawing tool. And the wire is made up in, let's take a simple geometry in here, some sort of a rectangular form. So in this case, it's easy to find. So in this case, I have L is the length and W is the width, and you can actually take it to square if you like, L times L. So it's going to be L squared, the area of this region. So if you're trying to find the moment, you can find the moment in here by just making sure the end of current and doing all of the others. It doesn't matter. I have the magnetic field now coming from in this direction, this way. So this is where B is. Okay? That's the direction of the magnetic field in that region, which way it's pointing. Now the area itself is L times L or L times A, so there is an area in here, it doesn't matter. So the flux of the magnetic field is going to be B times A. Because A, the only thing I'm going to do in here, I'm going to spin this one in here, okay? I'm going to force this one to turn. And usually I can use water for that. So the water as it falls, for example, it can take the turbine and make it start to turn. So somebody has to actually turn this thing. It's like the wheels on the bicycle, for example, when you have that dynamo, which is attached to the wheel. So you're actually the one who's making the turning the thing to make electricity. So now, let me take it, because I flipped it this way, it's much easier to do it this way again. So this is the area A. This is the direction of the magnetic field. I took it this way, and they make an angle between them, which is theta. So B times A, which is the flux in this case, I already integrated over the surface, and I know the magnetic field is constant. So the only thing that changes in this case is the surface, and it changes not because of its dimension A, but its orientation. So this flux at the end is going to be B times A, and B times A is B times A times cosine of the angle between them, theta. Okay? And at the end, I mean, the geometry involves that you connect one part of the wire to so you make it a little bit this way, and there is a brush actually that is attached in here to make sure that the contact, because this is spinning very fast. So there is a hair brush in here that is in contact, and there is another one in here that is in contact, and in here actually you will have a voltage, permanent voltage in here that is actually changing in direction, because sometimes the cosine theta will ensure of that change. Anyway, let's make sure that theta changes as a constant rate, at a constant angular rate omega. So that theta is actually uniform. Let's say, for example, the water is steady, falling steady, and as it's raining steady in here from the fall, basically the angle with which this thing is spinning is constant. Basically, the rate which is spinning is constant, and I'm going to call it omega. Okay. So this is just like the uniform motion that you guys had, the uniform circular motion that you guys had in physics 1. So the flux of the magnetic field phi B then is given by B, which is the strength of that bar magnet, times the area, which I just called it L times R or L times W, or even if it's a pi R squared, it doesn't matter how the shape I have it, it's a finite area that they can measure, times the cosine of omega t. Now, the EMF, and I don't care about its sign right now, okay? But if we wish to, you can put the sign if you want, and then the EMF that is going to be produced in here, in other words, the voltage that you're going to have actually, is going to be given by minus d derivative of this flux with respect to time. Can anybody tell me what this derivative is going to be? B is constant. A is constant. So the only thing that is changing is the cosine. What is that derivative? This should be easy.
Sine theta.
Okay, with a positive sign, because the derivative of the cosine is the positive. So it's going to be B A. Do I pull an omega or not from that cosine? Do we have an omega out of this place?
I think omega is still constant.
Yeah, but then when you take the derivative with respect to time, you're not doing the derivative with respect to omega t. You remember the chain rule?
Right. Okay. Yeah.
Okay. Yes. Somebody else made a comment. Let me check. Yeah, but you have a negative already. So Jonathan is saying, isn't it negative? Yes. Okay, good. So there is a negative times negative, so it takes care of that negative. Even if it doesn't matter. So basically what we have an EMF now, an electromotive force now, that seems to go into basically periodic behavior. It seems we have a current now, or battery now, that has its power source now, is this is the voltage that you have in there. So let's call it V naught in here. And this is sine of omega t. So if you don't like the negative sign, just basically wait for it to pi cycle. If you don't like the sine function, basically, and you would want to behave it like a cosine function, just like wait a quarter period, like basically pi over 2, and omega t is just pi over 2, and the sine becomes a cosine. The two functions are all similar. Basically, minus sine omega t is the same as a positive cosine omega t, or the all you have to do is just wait the appropriate amount of time, and the sine will convert to cosine. So basically, they're all similar. They transform into one another basically with their thing. So this is basically what we have. This is what we call an AC current. So now the current. Now remember, I have just voltage at this point. That flips sign. Sometimes it's positive this way, sometimes it's negative. Do you guys see that? Because of this sign function. Sometimes I have the polarity in here is positive, sometimes it's negative. If I wait a little bit longer, they will change. This becomes positive and this becomes negative. And if I wait a little longer, it's going to flip signs again. Do you guys understand that? So this polarity is changing. So if I put something attached to it, if I put a resistor in here, that resistor or light bulb in here, light bulb is going to behave. So the current is going to be running at some point this way in it. At some point, it's running in the opposite direction. So it's an alternating current. Do you guys understand that? Basically, depending, it doesn't matter what load I put in it, that load will basically, in other words, what kind of thing I put attached to it, computer or something, that computer will see the current going in one direction, and sometimes the current is moving in the opposite direction. So, the class is going to end in about a minute, I guess. So let's finish this point quickly, and then we will finish the rest of it on recording. So basically, this is how the current looks like. I mean, the voltage at least. It's a quantity that changes periodically, okay? Again, my point in here, if I wait quarter period, it's going to be actually a cosine function. If I wait for it a full cycle, it's going to come with the opposite, basically, phase, and so on and so forth, okay? So, we're going to stop it in here. We're going to pick up this thing in here. We're going to find we'll try to understand what that V0 is. V0 is about 170 volts in the United States, and omega is the frequency for that one is about 60 hertz in the United States. And when you do the effect of basically the RMS in the United States, you will find it later on to be about 120 volts. So that's something that is a common application here in the United States. In other countries, they have different voltages. They have 240 for the RMS for their V0, not this value. And the frequency is a different number in there. So for some reason, we don't have a lot of people. We don't have basically more than half the class in here, and that is kind of odd. And I don't understand what happened. So we're gonna try to reach out to them.
They couldn't find the link to the class.
Oh, it's not on. It should be on Canvas.
Well, it is. That's how I found it, but it's you have to scroll back from Tuesday. I think they don't realize it's just the same link as it was before.
Yeah, I'll communicate that the link to them is not changing at all. It's the same link. So, okay. And they should probably bookmark it on their web browser or something like that so that they can go to it. Anyway, I will repost this one today or tonight or something, and watch out for the homework assignments for this part. And we will see how this goes, and probably the recordings will expedite this thing. And I really need to make sure that people are ready for the exam too. Any questions? I know we're talking about a minute past the allotted time. Any questions for this part so far?
No, I don't think so.
Okay. Okay, as guys, I see you guys, and I will reach out to you guys. Please follow on YouTube. I post a lot of things, and sometimes, like I say, I really don't go immediately and tell you about them, but I'm hoping that you guys are getting the notifications from YouTube saying that the new posting is up. And of course, not all of them are in your class, but if some of them are related to your class, please do have them. Like one question that popped up last time from Physics 1, actually, and I went back and I did the connection to chapter 28, basically when we were calculating the circulation of the magnetic field. So I did that as a video instead and basically posted on YouTube, and I'm hoping that you guys see that to have a clear understanding on how you do those calculations, because some of this stuff, I know you did it last semester, especially with what's going on, probably you guys forget it and things like that. Okay. Please keep in touch, okay? And stay safe and be safe and take care of your family and yourself.
Thanks, Professor. Have a good one.
Thank
Okay,
you too.
Thank you, DJ.
Thank you, guys. Bye.